Okay, so now we're going to look at the derivative a little bit more mathematically with specific values here. So here's a very basic position as a function of time graph, and you can see that, we already know that the positive constant velocity that's being shown here is going to be listed as a horizontal line on this graph. Okay, so that's what we were doing in the last video. But let's review a little bit of basic mathematics here. For a generic XY scatter plot that is a linear relationship, we know that we have the equation y equals mx plus b. So for this graph, we can replace the variables to make it specific for this for these specific physical values. So on our y-axis we have position. For m, we know that it is the velocity, and we can calculate the slope of this. This is 10 minus 2 over 4, so it's 8 divided by 4, which is 2 meters per second. And on our x-axis we have time, and our y-intercept is 2 meters per second. Okay. So because we already know, just from calculating the slope, that the velocity is 2 meters per second, we can already mark what our velocity time graph is going to look like, because we already know that. Now we just have to take a little bit of initiative and think about that. By taking the derivative, what you're going to see is that you're also going to get that value. Okay, so the way we take the derivative is we basically use a formula. It's a standard formula that works for almost all derivatives. I'm trying to remember the proper way to write this. This equation is given to you as a function of x, right? So it is x is equal to some constant, which was the constant slope, times t to the nth power. So this is t to the 1. We could have t to the 2, squared relationship, t to the 3, anything, okay? And actually that's going to be plus some constant, but we're going to leave that out of there because you're going to see what happens to constants. So this is the generic form. And to take the derivative of this, we use another equation. So this is defining what our variables are, but the derivative with respect to x, dx, dt, so this is going to be the derivative of x with respect to t, is going to be the n times the constant times t to the n minus 1. Alright, so what we do is we take this n, we multiply it to the outside, so it's n times c times t, and then what we do is we just subtract 1 from the exponent and rewrite it. So if we look at this equation right here, if we take the derivative of this, we have 2t to the n. Right? So that's t to the 1. So what we're going to do is to take the derivative of this equation right here, dx dt, we're going to take 1 times 2, which is, I'll write it out the long way, 1 times 2, so it looks like this, 1 times 2, to the t to the 1 minus 1. Okay? And then we do the same thing to this right here. So this is actually a t to the 0. So 0 times anything is going to be 0, so that we'll find that the derivative, we can actually write that out right here, dx dt of a constant is 0. So of c is equal to 0. So the derivative of c with respect to t is equal to 0, and that's what we just did here. Okay, so what the derivative with respect to t gives us is 1 times 2, which is 2, t to the 1 minus 1, which is t to the 0. T to the 0 is times 1. So we end up with the derivative of x with respect to time of this specific relationship will give us the value of 2 meters per second, which is going to be what we're going to see on our graph right there. So you can see that it is going to work out graphically. I mean, and it will work out in more complex situations, but it's easier to see a very basic situation like we just saw. So what we have to really be comfortable with is that equation dx dt of some function x, okay, is going to be n times c to the t n minus 1. All right, and this is another way to express this notation here. It's kind of like the derivative with respect to time of some function x with respect to t. So if I give you a function of x with respect to t, so let me make one up here. So I'll have x of t is equal to 4 minus 3t plus 4t cubed. So this is going to give me, if I plug in any t into this equation, it'll tell me where that particle is. Alright, so if we want to take the derivative of this, we're basically taking d dt of x, and I wrote that wrong, x of t, okay, which would then be d dt of 4 minus 3t plus 4t cubed. So we're taking the derivative of each of these terms. So the derivative with respect to time for a constant is 0. So this one, 4, derivative of 4 is 0. Okay? Now the derivative of negative 3t is, the negative stays there. We can see here that it's negative 3 is our constant. So we write that down. We take the n value, which is 1 here, and multiply that to the outside. So we have negative 3 times 1, which is negative 3, to the t, it's t to the n minus 1. So 1 minus 1 is 0, so that's t to the 0, which is 1. So the derivative of negative 3t is just negative 3. You can see it just drops a power. Plus 4t cubed. So we have to multiply the constant by n. So our n here is 3. So it's 4 times 3 is 12 times t to the n minus 1. So it's 3 minus 1, which is 2. So this is the derivative of x with respect to t, which is basically our velocity function. Now we can go and do that one more time. We can take the derivative of v with respect to t to give us our acceleration. So this is now v. So if we take the derivative of v, which is the same thing, derivative of 0 is 0. The derivative of a constant is 0. And the derivative of this is going to be n times our constant, which is 2 times 12, which is 24, t to the n minus 1. So it's 2 minus 1 is 1. So our acceleration function here is 24t. And that's the basic derivative. On the next video, I'm going to work through a few examples, again, just using a formatting tool, which is this.